Okay, folks, let's get started. Hi, everyone. Hello.
Hello.
Hi, my name is Reza Khami, and I'm an associate professor at the Department of Civil Construction Environmental Engineering. I've been an affiliate faculty with the CSRC since 2019 when I joined SDSU. But I'm not here to introduce myself. I'm here to introduce the great speaker for today. Dr. Juhyeon Bae is an assistant professor in our department, in the Department of Civil Construction Environmental Engineering at San Diego State University. He received his PhD in civil engineering and a graduate certificate in computational neuroscience from the University of Michigan in 2024, a year ago, almost. Dr. Bae's research lies at the intersection of construction engineering, wearable biosensing, and artificial intelligence. His work aims to enhance safety and human performance in construction through interdisciplinary methods. For example, he integrates wearable sensors with behavioral science to empower construction workers to self-manage physiological risks such as fatigue. More recently, Dr. Bae has expanded his research to explore the mental health dimensions of construction safety, including stress, depression, and suicide through participatory and AI-driven approaches that leverage wearable sensing and large language models. On a personal note, he's a good friend of mine, very approachable and friendly. And I think he also looks for students, so I would suggest that you listen carefully and then approach him after it's unfortunately, I have to leave to pick up my little one from the SDSU daycare, but I have seen his presentation before. I'm sure you're going to enjoy that. The floor is yours.
Thank you so much, Reza. Thank you for the great introduction. And good afternoon, everyone. Thanks for showing up today. It's gonna be rain, I guess.
No, don't say that.
Don't say that. Okay. So I was just worried about people running out home. I found driving in San Diego in rainy days quite right. So
You know why? Because people here don't know how to drive. So then
oh yeah,
in the rain, it gets really
oh yeah. So anyway, I'm very happy to be here today to give a talk about my research. And today's topic is gonna be how I apply wearable biosensing integrated with behavior science to make our job site more safe, like a construction site. And today's talk is going to be a relatively high level because I feel that we are from all different disciplines, and it's going to be more about application and integration rather than math or fundamental science. So I think everybody can enjoy it. Yeah. So before we jump into the detail, my research vision is how we can enable construction workers to help them make more informed decisions about their own safety, like self-managed safety, as well as how we can make them work together to prevent, to protect, to help each other. And my approach is to apply wearable biosensors and behavior science for that. And we'll be talking about that for the next 30 minutes. All right, so today's outline is I'm gonna begin with talking about some background, like safety issues in construction and how the wearable sensors and behavior science are relevant to address those safety issues in construction. And then we'll be talking about some applications of wearable biosensing for personalized safety monitoring. And we're going to focus on two important risks, fatigue and heat stress. And then we'll be discussing how we can expand those personalized monitoring to more team-based, peer-oriented safety management, how we can share those safety information among workers to make them work together safely. And I'm gonna talk a little bit about the research I'm doing right now, some keywords and some topics, and hopefully we can talk about possible collaborations. Yeah, let's begin with the background. So I assume that everyone here understands construction sites are risky, right? it's very understandable that because we see a lot of hazard and risks in construction site, electrical lines, sharp materials, and heavy equipment, they're all source of hazard. So for that reason, we have a lot of fatalities and injuries every year. Like 1,000 people die every year, and this is among the top fatalities in all industry. Like sometimes transportation industry got first rank, sometimes construction, unfortunately. And we got beyond the fatalities, we got a lot of injuries, like 170,000 injuries every year. And so researchers were trying to understand and identify what causes, what are most important factors in creating this kind of construction accident. And some findings indicates, okay, workers and safe behavior, this is really important because it is related to 84% of all construction accidents. Like, this is very intuitive because you can think about construction site, there are a lot of hazard and workers are not wearing the PPE hard hat. And if there is a falling object from the ceiling, it's gonna happen an accident. But if the workers were compliant in PPE wearing, like wearing the hard hat, the accident could be minimized or avoidable. And the second important factors was poor risk management, meaning that the accident is not just about workers' safety behavior. The management is equally important to prevent those issues. And the other factors are inadequate supervision, local hazard, and safety cultures. And what we can learn from here in this data is, what if we think about it in this way? Like, what if we can make workers work safely? Then how many portions of the accident could be avoidable? Or what if we improve some risk management? What if we could do the same at the same time with some technology, wearables, or behavior science? That's the motivation of my research, how I apply some wearable-based risk management and the behavior science to eventually make workers work safely. So that was some motivations, and I will introduce a little bit of limitations of current risk management, because it's always important to identify, okay, what's the issues right now and how we can address. And one of the important issues is one-size-fits-all approach. This is not bad by nature, but has some limitations. Like when we take an example of heat risk management, what we usually do is, okay, we know how the weather is gonna be during the morning and afternoon, then we can use this information to schedule the work and rest, like work rest schedule. And there are some guidelines, industry guidelines that, for example, under the cool weather, after maximum 45 moderate work, we need to rest like at 50 minutes, or under the hot weather, it's gonna be like maximum 60 minutes for light work, or less for moderate or high intensity work. So this is typically how we approach the management for the heat risks, and it is great and we need it, but we need to keep in mind that every individuals are different. Every individual has different physical capability and mental capability. So even for the same schedule, what they feel could be quite different. Like, okay, I'm very happy with this, and I'm capable of doing this job under this schedule, but some are not. But it is very hard to consider those all differences, because when you think about like a big construction site, there are 200 workers. Can we make 200 different schedules for all of them? No. Then maybe we can take an alternative approach that, okay, how we can better understand individuals' responses so they can self-manage those risks. So for example, if this is not gonna work for me right now, maybe I can take a look at some data on my, and maybe have a few minutes more rest to stay on the safe lines, something like that. So this is one of the main motivations of applying wearable sensors for construction sites. And once we get some ideas of personalized in-depth human response monitoring with the wearables, it becomes more clear that how we can apply this. Okay, nowadays there are a lot of wearable biosensors on the market, like we have earbud, like or smart rings, and EEG device, and Apple Watch, and some forearm attached sensors. There are a lot of there are a variety of wearable biosensors, and the status says that almost like 1/3 of US adults are already using wearable sensors. So it's not futuristic story anymore. It's prevalent in the construction site as well. So like Apple Watch, a lot of workers are wearing Apple Watch. And the market size is getting bigger, meaning that the wearables,
Do they pay attention to what the thing tell them? That is a different issue.
they put the workers.
Well, I mean, I've seen a lot of people wearing
Yes.
things, but do they actually follow the whatever they?
That's the beauty of behavior science. Yeah, that's the beauty. Like there's an intention for us, like to apply those technologies, but the reality can be quite different. How they buy in, how they adapt, those technology can be very complex issues, and that's why I'm approaching this technology with behavior science. Thank you. So the cost of sensors are getting cheaper and much prevalent in construction site as well. So there are many opportunities for us to apply those sensors to monitor diverse human responses like stress, strain, fatigue, and emotions, so we can get real-time, in-depth, individualized human response data. So the ideas of wearable biosensor for safety is how we can use this data wisely to make real-world differences in construction site. And when we take a look at some existing examples of such solutions, the Kengen is a famous company for heat stress monitoring and management, and those sensors allows workers to monitor their heat risks, like here. And also the managers can use the aggregated data, okay, the overheat risks over the job site or among crew teams or whatever, or job site level. And they can use this data to plan or intervene the construction work. And this is great, but what I'm thinking something is missing here is virtually all the construction work as a team. Like there are a few crew members who work together to complete this job. So they are typically the most closest physically, and they know each other very well. Then why don't we use those opportunities to maximize the potential of wearable biosensors for safety monitoring? So in that way, we can add additional layer of protection by sharing like a safety information among coworkers, so each other can know, okay, who are at risk, and if I can take actions for them, maybe we can have them stay safe. So those are what differentiate my research from our existing research or solutions. And we'll be talking about then how we can monitor fatigue and heat strain from wearables. And then I will be talking about some field study that I actually applied those solutions to construction site to see, okay, what makes changes and what changes are there. So next topic is going to be wearable-based personalized safety monitoring. And we're going to discuss the fatigue first. Okay. So the wearable-based fatigue monitoring is not a new there are available research on this field. So people were using like a wristband type biosensors to measure like heart rate, and they also did some survey measurement as a to label the data, like how fatigued they are, like a perceived exertion scale. And they put those data into black box machine learning model to make some predictions about how physical exertions are there, and so that they can approximate individuals' fatigue. And this works great, but I identified two limitations that we can overcome here. First one is the physical exertion and fatigue may not always align. So physical exertion means activity itself, how intense the activity, and fatigue is how I feel. So depending on physical capability, those can be quite different. And think about you work very hard for the last 3 hours, and now you are having some rest for the last 20 minutes. Then right now your exertion is just almost zero, but you got fatigue. So we need something that can directly address the fatigue, not the intensity levels. And the second is the black box machine learning models. So when it comes to safety application, it is very important to provide some predictions that can be trustable. So, but the black box machine learning models does not explain how those estimations, predictions were made. So I think we can do something about here. And this is what I propose to address those issues. Like I applied a bioenergetic models of fatigue from sports science, and conceptually, what it does is, okay, everybody has a unique bodily threshold like this, okay? Some young people have some higher threshold, and older people may have some lower. And if the physical intensity stay below the threshold, we are consuming oxygen to produce energy, like aerobic, like swimming. Then you can imagine that some athletics, they can swim 24 hours straight without too much getting fatigued, and because they have a lot higher threshold, and the physical intensity is relatively low than their threshold. So this is aerobic, consuming the oxygen. But when the intensity goes higher than the threshold, individual threshold is becoming more like anaerobic exercise, like when you do weight training. You can never do weight training for like 3 or 5 hours straight. You will get fatigued, right? So if we know those thresholds for every individual and how fast the fatigue and recovery occurs, we can easily track how individuals are fatigued. So that's the main idea of applying this model. But the challenges we address in adopting this bioenergetic model in construction applications are, this model is designed for steady and repeated exercise like a swimming. Then you can, if you know the speed, you can just easily estimate physical intensity, like a weight, speed, and height. You can easily quantify. But the problem is construction work is more like combinations of subtasks or regular, and more about changing physical intensities all the time. So how we can track? Can you observe? Are you going to observe how intense the workers are working for the overtime? No. The alternative way is we can use heart rate as a proxy of those physical intensity. When you do a very hard work, your heart rate is going to go up, or vice versa. So by applying wearable sensors for monitoring physical intensity, we can adapt those bioengineering models for construction applications. So this is the main ideas, and there are some steps for identifying individuals' threshold and the slope, how fast they are covering or fatigue. But I'm not gonna jump into too much detail here. So the main idea is we use wearable biosensors and do some perception survey for fatigue, and then use those data to find out individuals' threshold and the slope, and use these to personalize the fatigue model for individuals. So to validate this technique, I collected some data from real construction workers, like 36 workers, and each worker wore the wristband sensor for 2 days doing the normal work, and I also did some survey measurement to label the data. So here the IFO wristband is what I use for collecting the input data, the biosignals, and Swedish occupational fatigue inventory scale, SOFI scale, is something I use for the labeling. And so I could collect 500 hours of biosignals around, and 204 SOFI scales that I can use to validate those techniques. And I use leave-one-out cross-validation scheme, like, if one subject has 5 observations of SOFI scale, then for each iteration, I take out 1 observation for testing set, and another for the rest of 4 for personalization, like finding the slope and threshold and evaluate the errors, and repeat it for each data observations across all the subjects. So we can evaluate the generability of those techniques. And the evaluation metric I use is mean absolute error. So mainly just absolute difference between the prediction and the error. And the results show that our technique has mean absolute error of 1.06 within 0 to 10 scale. And you can see how the scale looks like. So like 5 point is moderately fatigued, and 7.5 is very fatigued. So the errors within like this much which does not affect the interpretation of the fatigue levels. So demonstrating the field applicability of our technique. And we also did some correlation analysis, like this dotted line is meaning no errors, and our trend line from our data is like this, which shows quite correlations. So those are some validations, and I did another additional validation check, like face validity check, how our technique can work in real world. And so for that, I attached the camera on the hardware while they're working, so we can see what they're doing while we're collecting the data. And for example, this yellow area is the fatigue levels, how they're fatigued. And these lines are like a heart rate, the physical intensity. And this red line is gonna be individual's threshold, okay? Then when we take a look at here, like around 8 a.m., the workers were doing material measurement and preparation, which is like low demand. And you can see that almost no fatigues are here. And their heart rate goes like around very low. And when we see here, the workers started to do some concrete placement, which is because of high demand. But he just started, so the fatigue did not accumulate too much, but the intensity started to go high. And here After some high intensity work throughout a couple hours here, the workers are resting right now, like eating some bread. So intensity is very low, but still the fatigue is accumulated. So those shows how in real world the technique can work to understand individual fatigue. And any questions so far before? Yeah, sure.
So I had a question about the data set. So do you consider different age groups in the data set? Because you mentioned that like somebody who has an older age might be more susceptible to getting fatigued much easier.
Yeah.
Than if someone younger, they can have a higher threshold. And also like what about if they had like some pre-existing medical condition, like a heart condition, but they're a construction worker? Was that also considered?
Yeah, so for the second question, we did some screening questions before hiring the participant. So they were all healthy individuals, but with different age groups. And we really wanted to do some comparison between like the threshold, and we see noticeable differences in the threshold between the age group, but the number of participants was not enough to do some statistical analysis. But we see the notable differences. But not always, because some older workers with a lot of experience, they are more like healthy than novices or something like that. So it's not always, yeah.
And also like when the participants are on break, if so low demand task but fatigue still remains, so how long is the recovery period for them to be fine to be able to like go back and do some demanding work? Is that also monitored as well?
So for now, we don't have like some method to predict, okay, what is the minimum required recovery, but at real time, you can see your fatigue, and there are some maybe guidelines we can provide. Okay, for example, when fatigue is over like a 40 out of 100, then you need to be cautious, but you don't have to stop the work. But if it goes up to like a 70 or 60, then you can have 5 minutes. It makes differences. It makes differences, yeah. Right, then let's talk about the second topic, heat stress, heat strain. But before we talk about it, how many of you are aware of difference between heat stress and heat strain? Because that is sometimes interchangeably used. But we need to differentiate here. The heat stress is external heat load, like how hot is outside, the temperature. But the heat strain is your bodily response, like how my body feels with those temperatures. So the more accurate way to understand our heat risks are looking at the heat strain. Like, and some examples of heat strain is your core body temperature, your body inside, your temperature inside the body, not skin temperatures, and not temperatures outside. So there are some efforts to explore the opportunity to apply wearable sensors to understand heat strain. And there are some rationales here. When you get hot, your body starts to get sweating, and your fluid volumes are increasing to transport the internal heat through the skin to the outside. And those bodily changes can manifest in some patterns in your skin conductivity and patterns in your fluid volumes in PPG signals. And if you apply some signal processing and machine learning algorithms, then we might be able to predict core body temperature, okay, without using rectal recording in construction site, you know. So we do use response sensors that is more practical. And there were very recent studies on this topic, like applying deep learning models and wearables to predict core by temperature. And I find two limitations we can address. The first one is going to be the existing study. They are validated in with simplified activity protocols like 20-minute exercise in treadmill, 10-minute rest, 20-minute exercise, 10-minute rest, and you see the potential differences in construction work. I already thought about it, regular and dynamic. And they were done in the say lab environment with fixed like temperature, humidity, and etc. And we need some research to validate in the real job site to say that, okay, we can apply this into real construction site, not just potential, it has some field of applicability. And the second issue is, okay, when we collect, so we want to validate in the real construction site, and a potential issue is data scarcity in high temperature, like the data measured when workers have like an 84, like high body temperature, because the construction site already has some routine management strategies to prevent workers reaching to this point. So when we see the real world data, it will look like this with little data around like a high temperature here. And the problem here is when we use this data to train machine learning models, it will be biased for like a normal temperature ranges here. So meaning less prediction accuracy here, where we need the most accurate predictions. So there are some challenges in the data side to address to evaluate the field of applicability of this work. So this is what I propose to address those issues with 3 different steps. Firstly, we will process the biosignal, especially the PPG and electrothermal activity and skin temperature, and we filter out some noises and decompose some like EDA signal into more meaningful features, and we segment the data like every 2 seconds to put it in the machine learning models. And then we apply some generated adversarial network-based data augmentation to create some synthetic data here to increase the predictions around the high temperature ranges. And then we can train the model and evaluate the performance. So the first step involves some signal processing pipeline. I apply some moving average high pass filter and some EDA decomposition here. The EDR is electrothermal response is more like immediate reaction or bodily reaction to some changes, and this is more like stable changes in your body, in your skin conductance. And I also process some PPG and skin temperature signal, but I believe we don't have to jump in too much detail on here. And this is the architecture that I propose. It looks complicated, but only 2 modules that we need to talk about. The first one here is conditioner plus certain GAN technique, which means conditioner means, okay, we're going to generate the data, the synthetic data, but with some conditions. And the conditions like, okay, I will generate the data over 37.5 Celsius degree. So because I need some data around high temperature range. So that's why there's a C. And so we apply the conditioner GAN here to create some synthetic data and use those real data and synthetic data to train multi-layer neural network models. And then the second thing here is I apply the symmetric smooth laws. So simply speaking, I give more penalty. So when you train the model, I give more penalty when the model create some errors when they predict high temperature data. So because it makes sense that the risk, the potential consequences when you make errors in high temperature data is much higher than overestimating a normal data. So I apply those two different techniques to see how we can ensure the model performance with the limited data scarcity. Yep.
Oh, my brain melted, but I have another question. If you consider the close, do you actually consider the close? Because the heat indexes, those calculations depend upon not only the temperature and dew point and stuff like that, but they're, what type of clothes you're wearing.
Yeah, so the closing factor is so important. The bodily response can be significantly for when you write like maybe t-shirts or some more PPEs. Like when you do work in some confined spaces, high temperature, you need some more protective equipment, and it makes differences. But there were 13. So in this model, we don't use the closing factors as an input, but it's very easily done by just adding one more input with binary, like a more deep close or a light close. And when we validate those models, we had like a 13 open source workers. We'll talk more about it, but they were wearing all the like light t-shirts because it was measured, collected during the summer. So the closing factors were not considered in this kind of training and data collection. But I do understand and I do make point on this is one of the more important factors in addition to the temperature, the closing,
Also the fabric is not
Yeah.
light versus thick.
Yeah.
Yet they're both on
Yeah.
different materials.
Yes, it makes differences. Yeah.
Do you consider the input data, wearable biosensors, do you consider this stochastic?
So I did some like a distribution analysis for something like that. But can you be a little bit specific on like what's stochastic?
Well, just stochastic in general, because what you're doing is you're using some sort of neural network, and anything that's stochastic. Now it's bounded.
Yeah.
But if it's stochastic, there's always a chance that your neural network could hallucinate. It's less of a problem than the newer large language models and stuff.
All right. So I didn't do any stats for stochastics, but some of my thought is our body temperature is like a more strictly controlled, like stays around 36.5, maybe most of the time, a little increase or not less increase, little like a lot less than like by temperature, normal by temperature, but it don't go like a 39 or 40 or 42, which is unrealistic. Yeah.
They're dead.
They're dead. Already dead at 40. Yes.
Now, just out of curiosity, because if you're doing any predictions, right? One way to solve a lot of the problems that machine learning has is, that seems to be really popular nowadays, is called retrieval augmentation generation,
Mhm,
RAG,
yeah.
or whatever. And it looks to me that you're the expert, you're the retrieval augmentation generation intelligence. And you noted that you probably needed synthetic data.
Mhm, mhm,
So then you actually went and augmented
mhm. Process, yes.
the process. That was just a comment.
Oh, yeah, thank you. Thanks so much.
So you're the RAG intelligence.
Thank you.
Congratulations.
Right, so yeah, let's keep moving. So we needed data. So I went to the construction site again during the summer and collected the data from 13 construction workers and each 8 hours doing their work. And I applied the wrist-worn sensors to collect the input data, BPG, EDA, skin temperature, and also I applied the ingestible pill sensors because we need to know the core by temperature. I don't want to use the rectal every minute to train the model, right? So I alternatively use this ingestible sensor, and it will stay when you swallow the sensor. It will stay in your body stomach for 2 days. In the meantime, the sensor will communicate with the lower ear to send out, okay, what is the body temperature every 10 seconds. So, not everybody is happy with swallowing that one. That was really, really challenging in finding the participant. But yeah, anyway, this is something, interesting point here.
But, you think 13 workers is enough for data collection?
That's a really challenging question. Yeah, it is very hard to say one number is enough, right? And it depends on the domain. Like for images, it's very easy to collect images from like 1,000 people with different handwriting styles or whatever. But what is like a rule of thumb in this kind of human subject data is 13 is not many people would think is going to be enough, but it is good for testing some preliminary analysis. But if you have like a 50, for example, and the researchers in our field is going to think like, okay, it's going to be quite good number. And we also need to think, see how many hours the data were collected. So the amount of data from how many participants would be considered together, but I think 13 is good for preliminary analysis, and we need some alternative approach rather than finding 100 construction workers who will swallow the pill sensors. Maybe
You have to talk to the Teamster.
sorry,
You will have to talk to the Teamster.
Teamster
Yeah,
unions, yeah.
go to the career STEM fair or whatever. It was the one about 3 weeks ago, and there were maybe a dozen or more.
Mhm.
I'd say about a third of the people there were giving out squeeze toys that were bulldozers, hard hats.
I know
So you can guess what
Yes.
they were construction people. And feel free, you have my permission to hustle those
Can I get your name?
people to volunteer their workers as victims or whatever.
I think we our construction program is very well connected with the companies. Like this week, we had a career fair just for our department. There were 60 companies.
Oh, okay.
So
So this is a great place
Yeah.
to do this kind of
but I
research.
think even if they volunteer the workers have to,
Yeah,
they cannot be voluntold.
Yeah.
right?
no.
But I agree that talking to the union, for example, I was talking for my own research with the carpenters,
Hmm.
and maybe if you go through a group like that, they would be more willing to,
Mm.
we can talk about that.
Yeah,
too.
sure.
But,
Or
but
unions.
the workers,
Mhm.
the
Yeah.
workers have to agree.
That makes sense.
One last quick question. It's bad enough to collect data, but how did you get ingestible pill sensors through the IRB, the institutional?
That is
Review
really,
Board?
really challenging. We had a few rounds of revisions, like okay, so can you provide data, like how many people already use that and what is incident rate, something like that. And luckily, the companies, they need to sell the product and they open the data, like okay, we tested this more than like 100,000 people. There were two adversary effect. So it was quite safe. And IRB is, is most challenging things for human subject studies. Yeah, it took a couple of months actually, and we also
Month only?
yeah. Wait, typically for one IRB it's gonna take 2 or 3 weeks. That's it. But it took 3-4 months because we had to find practitioners who can create the screening questions together and create some protocols for safer data collection, something like that. So we had like a back-to-back conversations with.
I think we have made a lot of progress
Uh-huh.
in this IRB because I've been here for a while and it was about a year or more to get something through.
Yeah.
Just out of curiosity, how much were the participants compensated
Oh,
for injecting something
So-
inside it? Yeah.
so how much would you think is reasonable? How much you? Any guess?
How long would it monitor for?
2 days.
This one day.
One day.
One day.
Probably a coupon for McDonald's, probably.
McDonald's. So yeah, it was the compensation was $100 for one day.
That's pretty good.
Per hour?
Oh no,
Per day.
for the day, $100.
You notice how the incentive that the companies provide, they look like great, but there's very little what they really give.
A little story about it is, I actually collected data when I was in Michigan and I do my PhD study. And for the first summer, I couldn't find one single participant throughout the summer, even though the companies helped us a lot and we distributed flyers and meet people, but we did everything, but there was no single participant. And after 1 year, I was rejected by like 20 people because I went to the site, stay and say hello, introduce myself, and I was trying to find the first people who are willing to do this. And after 1 month of effort, I spent a lot of time staying inside. And 1 month, I found one guy who he was a gateman, like who is working on the gate, controlling some entry stuff inside. And he just told me, okay, I'm the best person to do this. So I was very lucky to find him. And after he already did that, his friends started thinking, okay, this could be enough and easy money. So he brought one more friends, and this guy brought 2 more friends, and how it worked.
I thought that there was you open the gate if you swallow the pill.
Yeah.
Uh, Was it chocolate covered?
Chocolate cover? I didn't think about that. That was a great idea, but
Yeah, like this kind of.
Makes a
Yeah.
big difference.
yeah. And some worker, one day, a worker just brought one like a something wrapped with the paper, toilet paper, and he showed me, hey, look at this.
Did it?
But it was chocolate. It was chocolate. It was chocolate.
Okay, so continue.
Yeah.
We're interrupting here.
Chocolate.
Chocolate.
We need a chocolate.
Okay,
now.
I got more sensors in my lab. If you wanna try.
But
Okay.
it would be 100 per hour.
If I get all your meeting. All right, so yeah, we have a limited time, so I'm gonna go a little more better. Okay, so I evaluate the data here, and some findings. I compare 4 different setups. Okay, just pure NLP model, and I added the symmetric loss only and GAN augmentation only, and symmetric GAN augmentation both, and compare the performance. And the mean absolute error, the baseline model and the final model was comparable, but the mean bias was quite different. It was underestimating because we lacked the data on high temperature range. So after I applied symmetric and GAN augmentation, the bias was quite we see the improvement and as well as the mean absolute error. And the graphical representation is this is pure NLP model, and here we are bad at predicting the high temperature. When we apply a symmetric or GAN augmentation, we got a better result here. But eventually, after applying both techniques, we have more accurate predictions for like a data over like a 38 Celsius degrees here. So it shows some differences. And I'm also doing some more analysis with the data to apply some more advanced deep learning models, as well as subject-independent validation, like even subject outcomes validation. And those are some preliminary research results. So for some subject, the prediction is quite well aligned with actual. The yellow is the core temperature, and the black line is ground truth, and quite well. But some subject we see some errors because of the limited subject number or etc. So maybe I'm here in San Diego, and I might be able to do more research. I was in Michigan. Summer was only 2 months, and I had to find people with a limited time. But I have perfect place to do more heat research here, right? So actually, this was the main topics I wanted to talk about today. But yeah, so the next question is, okay, we got fatigue and heat strain data, and how can we make best use of this data to improve workers' behavior and make them help each other, protect each other? And my approach was
You got 5 minutes.
5 minutes. Okay. So yeah, I apply some theories of social norms, okay, as mechanisms to translate those data into meaningful behavior. So, like the workers, we wear the wristband sensors and connected with mobile app, smartphone, and in the cloud server, this data will be analyzed to predict fatigue and heat strain, and we will send them out to coworkers, like a share, where each one's fatigue in the mobile app. Only micro members, not others, like not managers. So here, And then we have some mechanisms how knowing coworkers at risk can lead to helping behavior. And what I expect from those mechanisms is stewardship, like actively protecting each other, helping, assisting, voicing concern, speaking out some safety issues, because I know who are at risk. So this is mobile app I developed, and like when you connect your app with response sensor, it will display fatigue, heat strain, and heart rate. And here, those coworker safety risks are shared. So this is the core module. And I also provide some actionable tips so workers can naturally make any actions. So I did some tests. I don't have time to explain every detail here. I did some field tests with those mobile apps, and I'm going to share some findings. So this is survey measurement I use to measure helping behavior. I have some examples here. I protect my crew members from safety hazards or something like that. And some findings, quantitative findings I got here is the red line is intervention group who used our app and response sensor. And the control group is they just did survey measurement without using any technologies. So I compared, and the risk information sharing was activated on day 6. So we can compare before and after the intervention. And we see the increase when we activated the risk information sharing. Here, the workers are more likely to help each other when they know co-workers' risk information, even though the access, my coworkers are a little fatigued, but just the fact that I know how others doing, it gives me more sense of team safety, like more obligations to help each other, and stewardship. We see the increase, and some statistical tests shows mostly the p values under 0.05, except the voicing concerns. We don't see immediate increase in the voicing concerns when the risk information sharing was activated, but eventually we see some improvement. And I also did some interview with the workers, and some important findings is I saw some instances, the real instances that workers showed their stewardship. For example, I called them, it says you're tired and you might need rest, slow down. So this is real dialogue from construction workers. And also they reported that they are more aware of how they are doing with their fatigue. So it gives more visible information about your fatigue. And the third one is gonna be I'm gonna skip those themes because we have another slide here. But there were diverse viewpoints about sharing personal data. We can talk about later after this. Yeah. So what I'm envisioning right now for my research is I'm particularly interested in wearables and AI and robotics and how we can translate those potentials into real-world meaningful improvement, like safety dimensions and mental well-being and productivity. And I'm gonna take an interdisciplinary approach, like how we can combine psychiatry to address the mental health dimensions and neuroscience, computer science. So I'm forming some interdisciplinary teams to apply for multiple grants. And what I'm mostly interested in right now is mental health issues. So a lot of people suicide in construction, even more, 5 times more than the physical accidents. 5,000 people died. And I'm applying wearable sensors to monitor individuals' depression and anxiety and stress, so they can self-monitor and they get some support from that. And also, I'm training some chatbot to tailor to construction workers, so they can have conversations with chatbot to improve their mental health literacy, and they can get some immediate support when needed. And also, I'm also interested in applying wearables for blood sugar monitoring, because what they eat in construction site is very unhealthy, but at the same time they work really hard, and their lifestyles after the work, they drink and they do some drug, or the lifestyle, eating behavior, and their work style and their blood sugar, there might be some implications in these interactions for their cardiovascular health. So those are some research areas I'm focusing on right now. And yeah, that's it. That's it. They are my collaborators, including my PhD advisor and some collaborators in the sponsors. Yeah.
Well, thank you very much.